Hello everyone, hopefully you can hear me. My name is Robert Paxton and I'm the VP of Strategy and Performance for CTA Canada. So firstly, I'd like to thank everyone for attending our renewable energy webinar. We have over 200 participants, so really have an excellent representation from across the insurance industry, which is great. I'd like to first cover some housekeeping items before introducing the presenters and the agenda for the webinar. So please note that this session is being recorded and we will send all attendees a follow-up email after the presentation and give you a copy of the recorded session. That email will include a very short survey, which should only take 1 or 2 minutes to complete, but we'd be very grateful for your feedback. Just so that you're aware, all attendees are muted. So however, if you do have any questions that you'd like answered, please type them into the questions section in the drop-down menu. A number of attendees have asked us about continuing education credits, so I'm pleased to say that at the end of the presentation, we will provide you with the name and email address of one of our staff members that you can contact to receive your credits. In regards to the presentation itself, we're excited to share it with you today. It's a collaboration between our Canadian and UK teams, and we hope that sharing perspectives from both sides of the pond will be helpful for you. CTA has a great deal of global expertise with offices in over 30 countries. So we'll be looking to share local and global expertise with you in future webinars, so look out for those. The agenda for this webinar will start with an overview of technology with a focus on wind, biofuel, and solar. We will then discuss claims considerations, and then we'll have 2 Canadian case studies. Finally, we'll have about 10 minutes to answer any questions you'd like to ask. So we have 4 presenters for you today. Our first presenter is Ed Hillier. Ed is an Associate Director of Natural Resources, and he's based in London, UK. He's been in the insurance industry for over 15 years, and Ed's areas of expertise are renewable energy, both onshore and offshore, subsea equipment, and aquaculture. Ed will be joined by Neil Armstrong. Neil is an adjuster and surveyor, and he's also based in London, UK. Neil's expertise is in marine losses, and he also spent 7 years working as a professional skipper. Our first case study will be presented by Wally Matthews. Wally is an executive general adjuster, and he's based in our Calgary office. He's been an independent insurance adjuster for over 45 years, and he truly has a wealth of experience. Wally's areas of expertise are major commercial property losses, energy and liability claims, business interruption, and fire and explosions of any magnitude. Then we'll finish up with our second case study, which will be presented by Christopher Davies. Christopher is an executive general adjuster, and he's based in the Toronto office. He's been an independent insurance adjuster for over 35 years, and his areas of expertise are major complex losses, business interruption, cost of construction, liability and environmental breakdowns, and equipment breakdown. So now I'd like to hand over to my colleague Ed Hillier to start the presentation. Thank you.
Good morning, good afternoon, everyone. Thank you for the kind words of introduction, Robert. Yeah, my name is Ed Hillier, and for about the next 30 minutes or so, myself and my colleague Neil will be running through this overview as per the agenda on the slide there. And we're pretty much covering sections 1 and 2 of this. Now, I must say at this point, clearly the vast majority of the attendees are from the Canadian insurance community. However, I am aware that there are other members from Europe as well. And we hope that whilst the focus is clearly on Canada, there'll be enough transferable points that you will all get something useful from it. Okay, so moving on, the first question to really ask ourselves is why is it important? Well, if we work on the premise of the UK here, this is from a freely available source of information called Gridwatch in the UK. This takes the information in terms of power generation at 5-minute intervals and shares them to a public audience on the internet. If I could direct your attention to the second box on the top line called renewables, on this particular day, several weeks ago, when I checked this, we can see that approximately half of the UK generation at that particular point was coming from renewables, which I think if we consider perhaps where we were 30, 20, or even 10 years ago, that's quite a remarkable change around. And I dare say the reason why this audience is on this call today is because that point has not become unmissed. So why does it matter to Canada, brackets Ontario? I appreciate there are clearly numerous other provinces in Canada. However, for the purposes of this presentation, it turns out the only grid watch I could find for Canada was in Ontario. So you'll have to forgive me for that, for those in BC, Saskatchewan, etc. However, what we can see there on this particular day, which I must stress was early in the morning local time, hence the solar figures, but after nuclear in Ontario, we can see a very high proportion is wind and hydro, which for the purpose of this we'll call renewable. And also there was solar added onto that. So we can see we're also approaching perhaps not an unrealistically similar figure in terms of renewable generation in Canada. So firstly, you can see there's perhaps some clear similarities between the two. Now, obviously, where things differ slightly is clearly in terms of land mass. Canada, as we're aware, is one of the world's largest countries in terms of by land mass compared to the UK, which simply is a rock in the northeast Atlantic. For that basis, the majority of the European development is offshore, whereas clearly it's onshore wind we're focusing on here in Canada. I do mention the hydro in the first line here, and that is really to say it's not a new industry per se in terms of renewables, because clearly hydropower in Canada has been around for many years, and indeed, the technology probably stretches back in some form or other to the Egyptians or beyond. However, in terms of wind, as we can see there, the first onshore wind farm was in Alberta in 1993. And as we can see, it represents, on average, depending across the province year on year, of about roughly 4.5% of the national generation average. Now that is based, a lot of that technology on the bigger, newer developments is coming from European technology exports. And the reason I say that is principally because we'll touch on it later, but that forms the basis of the supply lines, and certainly where the technology and intellectual properties come from, because that's where it was principally developed. Now, again, all this information I'm sharing here is open source, and this comes from the government of Canada, but this is where this 4.4% figure comes from. If we take the outliers here of Prince Edward Island and Newfoundland and Labrador, we can see that the majority of it does sit in or around the single figures in terms of wind generation. We have done a number of claims in support of the insurance community, certainly in London, in a number of these provinces across the country, and certainly the most recent one was in PEI, the first one there. So we can see there's a very diverse but consistent share in the majority of those provinces. Now, if we're moving on to claims, the dreaded word here, I'm sure there are people who deal in pre-loss on this call, underwriters or brokers and the like. Sadly, we're at the grubby end, as it were, of the claim side when things go less well than they'd hoped. And so this view here gives us some of the things that we've seen both in the European market and also in the Canadian domestic market as well. Here's three generic kind of views of damage, broadly broken down into blade damage, electrical infrastructure, and then the drivetrain stroke gearbox failures. Blade damage itself, again, it tends to be one of those things which is perhaps more natural forces, act of God, that kind of thing, lightning strikes, strong winds, we see damage. Erosion is one of those things which becomes a little more esoteric on the basis that it tends to be more of a wear and tear point in terms of the fact it's wind-blown debris, which both either causes wear to the leading edge or the trailing edge of the blades. The blades themselves are composite and so forth. They either have to be repaired or replaced. But that we're not looking at claim specifically issues here today, but I just want to bring it to your attention that it's something we do see, and certainly on the older installations. Like any generation facility, it is worth naught if the power cannot be brought to the point of presence and therefore the end user, and therefore electrical infrastructure is key. We're talking transformers and such like switchgear, which seems from time to time to have a habit to burst into flames or fail, and with inevitable consequences which come with that. One of the other points we're seeing more of in Europe at the moment, and not necessarily with older equipment, is that of drivetrain and gearboxes. For those that are unaware of this, the anatomy of a wind turbine will be covered later in one of the case studies briefly. But the nacelle, which is the box at the top of the tower, which the blade's attached to, contains the gearbox or the drivetrain in general. And we have seen a variety of failures in that respect, which have proved to be quite costly and somewhat complex when it comes to policy responses as well. So what looks like quite a straightforward thing can have some relatively interesting wrinkles to it. Now, just focusing on a little bit more about my last point, which is gearboxes and bearings. Two sorts of real failures here. The early operation failures, commissioning early operations, when things go wrong, tend to be the point when, if there's manufacturing issues or that kind of things, they're shown there. As in when the equipment is stressed for the first time for an extended period of time, that's when things go wrong. However, curiously, we are now beginning to see midlife failures in drivetrains and gearboxes. And by gearboxes, I also mean predominantly bearings, because clearly roller bearings and their like form a key component of rotating machinery in this kind of equipment. What we are seeing is a phenomenon called, it's either referred to as white edge cracking or sometimes referred to as white etching cracks. This is a metallurgical phenomenon dealing with grain boundaries. We can see an electron microscope picture there of the white lines are the white edge cracking, as referred to here. And effectively, these are subsurface failures which occur in the bearing races themselves and cause large parts of them to fail. Now, the interesting point with this is that this, by any stretch of the imagination, is not well understood, and academics are still currently debating on what the causes of white edge cracking are, and frankly there are no definitive answers at the moment. So what we've found on a number of cases is it's not a cause, but it is an effect. And on the basis that the cause of white edge cracking is not well understood, we can probably all understand as insurance professionals how that can create somewhat of a challenge when it comes to applying policies, policy warranties, and such like, and or simply defining what coverage looks like under these policies. And there is also language being developed in policies to deal with specific warranties looking at these issues. Now, some of the opportunities and challenges that come with this is where that we've seen, and this is perhaps, we're talking onshore wind, and I'd refer you to to Canada and also North America for that state of the word. In terms of actually the concept to repair duration, clearly it's not a complicated structure. However, it's typically a tall structure, and typically probably in a fairly remote location. So what might be a fairly straightforward repair if it was taken in a metropolitan area, in a factory or other mechanical process or location, will take an extended period of time. With that also comes the supply chain. You'll be aware that I mentioned earlier that a lot of the supply chain or the intellectual property sits outside of North America or Canada and comes from Europe. And we've certainly seen instances where that has significantly delayed claims because things have had to be shipped both into country and then be moved cross country to be able to rectify the problem. One example comes to mind exactly of dealing with a wind farm loss, relatively minor, in British Columbia, which took place in the late autumn, and due to the snowpack, it wasn't actually possible to fix the issue until the late spring. Now, supply resilience is something which probably wouldn't have even been mentioned 3 or 4 years ago in a presentation such as this. However, a number of this audience may be aware of a manufacturer or supplier of equipment which was formerly known as Senvion. Senvion have got a large fleet of deployed equipment, both onshore and offshore, and went into administration approximately a year or so ago. This caused all sorts of issues, principally when it came to policy coverage, because there is now no manufacturer's warranty on any of this equipment on the basis that the manufacturer doesn't exist anymore. So we're looking, obviously, there's quite a few what appears to be challenges there, but maybe challenges are too strong a word. Maybe it's realities. However, also there's new technology coming to bear. Now, on the idea that this picture shows what is currently the world's largest onshore wind turbine, as in commercially available one, which is about a 5.3 megawatt unit, which is deployed on advanced testing in Netherlands here in that picture on this slide. What we're beginning to see is, on the basis that there is an economies of scale, the offshore turbines are moving very much onto onshore spaces. So what was taken as being a run-of-the-mill offshore turbine, 2, 3, 4 megawatt units 5–10 years ago, are now beginning to be seen as onshore units, which clearly, again, present perhaps opportunities and challenges both for the insured and insurers alike. Now, moving on to claim-specific points, we've covered a couple of these or touched on them loosely just now. Those amongst you will notice that that picture there shows a graphic in an offshore wind turbine. But given what I've just mentioned about offshore turbines moving possibly into the onshore space, or what were offshore turbines moving to the onshore space, now clearly there was a degree of transition here as well. So, looking specifically at policy-related claims issues that we see, policy warranties, as we mentioned before, we mentioned about the Senvion issue in that particular point. Manufacturers' warranties is a key one here, whether they exist or indeed do not. Numbers of events, and what in the offshore world is referred to as serious loss clauses, are also things which have taken more precedence these days and are looked at harder, but they do vary widely in policy wordings that we see, at which point they begin to bite and affect the insured's possible recovery under the policy. And again, this is just something which, as an adjuster, we see. I'm not commenting the rights and wrongs of them, but just simply to say this is the kind of things we see and should be considered when perhaps moving into this market. In terms of repair schedules, things always take longer normally than we first thought. It's the law of insurance. I think that's probably the way to look at things there. But clearly, location and the ideas of providing and supplying repair equipment or replacement equipment is obviously a key driver to this. And that then drives the costs. In terms of that, then that neatly dives into the time-based element of business interruption, or indeed delay in startup DSU. It's something that we see increasingly often. Maybe it's a sign of the times that often the business interruption here is perhaps a greater cost than the cost of repairs in numerous cases, and is something that we're well aware of, and therefore try and work with the insured to make sure that everyone is very clear on what the actual repair timeline looks like. Now, just as a segue into perhaps more of our world in Europe of what this looks like, and to see the similarities, and perhaps based on what we said about the cross-pollination of offshore to onshore technologies, here is a schematic which shows, broadly speaking, how the two align. The first thing you'll probably notice is they're broadly similar. There are turbines, albeit the turbines are at sea or on some form of platforms or supports. There are array cables, exactly the same as onshore ones. The only major difference is there's typically an offshore substation and then an export cable to bring it onshore. Now, clearly, that doesn't happen in terms of the onshore facilities, but you could look at the export cable as being the overhead conductors on pylons. It's a similar idea. So I think what we're saying here is it's not that foreign, other than the fact that there is the marine component to it. Offshore wind turbines, again, very similar to onshore wind turbines, just basically bigger is the best way to look at it. Again, a lot of this stuff is driven out of Europe with the main OEMs, MHI, Vestas, Siemens Gamesa, Amalgamation, etc. The typical new deployments are 8 to 9 megawatts, maybe 10. Although there was a piece in the trade press recently suggesting that the new development in the North Sea on the Dogger Bank, which is to the east of the United Kingdom, has an order placed for 114 megawatt units. So clearly that is a substantial sea change again in terms of size-wise. And given the fact that these are multi-billion euro assets in terms of the wind farm developments themselves, they're now very much seen as investment grade assets in Europe. So things like pension funds, financial institutions, government bonds are buying into them, and that's the way they're largely being financed. But in terms of on a more operational level, the way they're running, it's again they're run from shore. All of the command and control is done through fiber optics, through the export cables, because clearly, simply, it's an expensive and somewhat challenging thing to do to bring support staff out to these turbines to run them. So anything where that can be minimised, it certainly is. And also, in a similar way to many onshore turbines, the health and diagnostic is run through the standard kind of SCADA data, which is something that we certainly look to use when it comes to claims to understand perhaps the cause and the effect of these losses. Now, we mentioned briefly that this is clearly offshore stuff, it's a marine environment. There is the requirements when things go wrong, or in fact even indeed to construct these facilities, is you need specialist vessels. This here is one such vessel. It's you can see the 6 legs, which basically makes it a mobile jack-up platform. And there are things in this to consider. You know, the origin, suitability, are they available, and the cost for these things. The reason I bring this up, because the direct comparison here with the Canadian market is craneage and lifting. All this is a mobile crane ultimately. And to build these larger onshore turbines, clearly you need a next generation of craneage. Is it suitable for the job? I.e., can it lift high enough? The availability, they're always in demand, and the cost of them undoubtedly expensive. So whilst there may be a minor issue going forward in a specific wind farm somewhere which requires some work in the cell, which is a relatively simple operation, getting the equipment in place may also substantially increase the cost, albeit on a relative basis, because it clearly doesn't involve the cost of hiring or chartering marine spread. In terms of some of the repair challenges, again, we're looking at a marine environment example here, but again, it's the same thing. It's transferable to the onshore environments, that being replacement equipment, vessels on the onshore. They need to read cranes, contractors, that's the same. Environmental conditions, absolutely the same. The only difference is clearly in the marine environment, we're talking about perhaps sea state, whereas perhaps on an onshore environment, it's more perhaps to do with access, soil conditions, and perhaps the likes of wind or snowpack, as an examples. But you see there are some very tangible and direct links between the two. And where we're looking in the offshore world to go to at the moment is a floating offshore wind turbines. This is a deployment at the moment going off of Scotland as a trial, but that shows where technology is going. So it's bigger turbines in deeper water, and the extrapolation onto the onshore environment is bigger turbines, perhaps in more remote locations. So that covers our quick overview of the wind industry in Canada. And so one of the things we'll talk about here is, and it's not escaped our attention in the UK, that certainly our view of Canada is there's a lot of forestry, there's a lot of timber cover there. And this slide here, which is taken from that biomass energy website, shows the relative forest cover across the country. Now, whilst clearly the United Kingdom is not blessed with the same amount of forestry, the bioenergy does exist in the UK in a similar way, and we get involved in it. I won't lie to this audience to say we do huge amounts of the work in the UK, but clearly it's our colleagues in Canada do more work at this, and there's some very interesting and tangible points that come from this. In terms of bioenergy that we certainly see in Canada and UK in general, there's that whole waste to energy point in terms of reusing waste combustibles to fire power stations or energy production facilities, and that also rather neatly goes with that symbiotic energy generation in terms of facilities that we see which uses offcuts or produces offcuts or waste combustibles. May quite often find it's useful to have a small facility which is able to turn that waste energy again into electrical power, either for their own purposes or to sell as an additional source of income, and also, dare I say it, to assist with environmental credentials as required, if there is indeed a way that's how they are measured. One of the interesting areas, and we've certainly seen this in Canada as well as in the UK, is the concept of repurposing fossil fuel power stations. Now, the point that we see on that is trying to move away from a carbon-based economy. And clearly, if you can't move away overnight, and clearly there are large installations in place which have a lot of capacity requirements for the grid. And so there is perhaps a realism which needs to be applied to this about how that actually is repurposed. But as an example, here is a picture of what's happening in the UK. This is a power station called Drax, which is the largest single power station in the UK, and a couple of years ago produced 6% of the entire national requirements of power generation. It's a traditional traditional coal-fired power station, which has been transferred to almost exclusively biomass now, and with the addition of a gas turbine, and will no longer burn coal as of next year. That said, what we also see is the idea of the type of claims, which is feedstocks, as in dust explosions and that sort of losses which come from that point. Rotating machinery, which is common of any power station, and I believe that our Canadian colleagues will be putting on a similar presentation to this in the coming weeks, focusing on that point, rotating machinery. And the big cost which comes out of this is the either DSU or predominantly BI costs on that point. And finally, on this section here, we're looking at the challenge and opportunity. Certainly in Canada, there's a large amount of lumber production and the likes. There is a proliferation of feedstocks, which perhaps we don't have in the UK in such proliferation. Those repair durations that we've got on principal generating assets can take a long time, and when they do, they have a major impact on generation, which transfers potentially into significant insurance claims. Now, at this point, I'm going to hand over to my colleague, Neil, to talk briefly about solar generation.
Hi, everyone. I'm Neil Armstrong. I've been working alongside Ed Hillier in the London office for the past 2 years, especially on small to mid-size onshore solar and wind installations, but also working alongside Ed on the larger offshore wind installations as well. I'm just going to go do a brief overview on solar generation and some of the kind of claims we see and the challenges behind them. Just to relate this back to Canada, we've got a bit of a graph here showing the rough potential generation capacity per province. Now, as you can see here, in terms of solar production, somewhere like Newfoundland and Labrador obviously has a much lower generating potential capacity than somewhere like Saskatchewan. And this is why it's really important in Canada. Now, in Canada, what we've seen over the past 10 years or so is from 2010 to 2020, the installed generating capacity in Canada has risen from around 250 megawatts to over 3,000 currently installed. Much of this is actually located in the province of Ontario, as they were one of the first to introduce a feed-in tariff, which really garnered interest in installing solar energy. So what are some of the issues we face with in solar claims? Well, the types of damage we generally see, obviously damage to the panels themselves is a big one, whether through meteorological events such as hailstorms, strong winds, lightning strikes, or theft or criminal damage. When we're talking about theft or criminal damage, we're often talking about the theft of the electrical cabling, which obviously contains copper and other metals which are very valuable on the black market. We're also talking about fire, whether that be from maybe a lightning strike, for example, starting a fire at the facility, or other things like, for example, for ground-mounted and more remote locations, wildfires, which we're seeing more and more of, especially in Australia and North America, which can threaten solar installations. We're also seeing electrical infrastructure failure. Now, whether that be on the site itself in the form of failed transformers or inverters, or off-site installations, for example, local substations failing, which means that the solar installation is essentially disconnected from the grid and therefore can't export any power. So why solar? Now, solar overall in Canada represents a very small proportion of Canada's generation capacity. So I believe it's around the 1% of overall generation capacity. However, some of the opportunities for solar power include the fact that you can install solar power relatively simply and in a short time frame, and especially in remote areas where you may have facilities that require power that it's a lot of it takes a lot of time and effort and cost to actually connect those to the national grid, whereas setting up a local solar facility to just power those individual locations is actually more cost effective. Some of the benefits of solar power as well in terms of claims is often if the materials and logistics are available, they can be repaired very quickly. Unlike, as Ed was saying earlier, with the turbines, wind turbines, you don't necessarily need large capacity cranes. Everything can be done with relatively small kind of plant and minimal labor as well. Also, the locations of solar vary widely. So, for example, we talked earlier about potential remote locations. These can present challenges in terms of similar to the wind turbine claims, in terms of maybe snowpack or just access to the location to proceed with repairs can be very difficult. However, we also see solar installations in urban environments on the tops of buildings where access is actually relatively easy. You've got the road infrastructure there to bring spare parts, and you've got generally more technicians in the immediate area as well. So it really varies depending on location, and repair. We do see repair duration varying massively between sites, and it often depending on the location. The other thing is, again, import of panels and materials. So again, it really varies depending on what manufacturer has produced the panels, where they've been sourced from. If they've been sourced locally, then often spare parts are readily available and can be installed quickly and easily. Whereas if you have a manufacturer based in Europe, for example, then obviously importing the spare panels will take time, which will potentially lead to increased business interruption claims. The other issue we face is aggregation of risk. So often, a lot of the time, we're seeing solar sites being set up, which are then actually expanded as the installers manage to kind of gain access and land rights to the surrounding areas. They're increasing the capacity of their sites and expanding their sites, and therefore we have a certain aggregation of risk where you're getting larger and larger sites in one area that could be subject to local meteorological events. And you could end up having an entire site taken out in one hit.
Thank you, Neil. So in summary here, we trust that's been a useful overview of the market from a technological point of view, and just want to bring up perhaps these 5 points for the audience to consider at their leisure. Firstly, and again in numerous areas, but not more in the offshore wind, is technology a major driver in this. We can see here in this slide next to us, there are perhaps some European-centric landmarks, the Shard in London, the Eiffel Tower in Paris, for size comparisons. But we can see the size of the wind turbines there, which are now currently either in deployment or being developed and will be deployed in the near future. For those in Canada, to be a little bit more centric, the 8 megawatt unit, which perhaps is not a million miles away from potentially being an onshore turbine in maybe 5 years' time, is broadly the same height as the Shangri-La in Vancouver, and is about a third the height of the CN Tower on the east coast. So clearly that's covered the east and west coast of Canada there. So hopefully that means something to most people on this call. In terms of energy storage, that's the next big change, and how the energy industry embraces that, whether that be battery storage, compressed gas, or the like, will be a game changer. In Europe, there's a huge amount of work going into this at the moment, as there is also in different parts of the world, about storing those who can actively and also store energy from renewable sources in a manner which is deployable at the time of their choosing, will be a game changer. Those supply chain challenges clearly retain and remain and will be extant for the future until this industry develops perhaps into more manufacturing bases in North America and Canada to support the growing industry there. But with that, these developments comes the developments of policy wordings as well. And then clearly policies are there to evolve as the risks for which they insure. And clearly the brokers on the call, I'm sure, will also be aware of this and will be thinking of ways to best suit their clients' needs, and insurers will be looking at ways to best quantify risk in these policy wordings. And that is something which happens forevermore. Clearly, the final point here is in terms of market composition. As these points become, or as these projects become bigger and these assets become more expensive, as it were, perhaps the local capacity in the Canadian markets may not always be possible, or the appetite for this risk in the Canadian market may not always be available, and therefore using or having access to other markets, whether it be in London, Lloyd's, and elsewhere, or indeed obviously North America as well, is going to be key. And we find that comes both opportunities and challenges, as there are different cultural norms, legal norms, and those of jurisdictions. So that concludes our presentation. We'll then now hand over to the first case study.
Good morning, good afternoon. I'm Wally Matthews. I'm with the Charles Taylor's Calgary office. I'm pleased to present a case study that we were involved in just last year. The claim that we're involved in involved an 88 megawatt farm. This 88 megawatt wind farm, just to put it in perspective, can provide power to 26,000 households. The height of the wind turbine towers are only 80 meters, nowhere near compared to what you've seen in previous slides presented before this. The reason that behind this loss was that the bad guys just wanted to have a financial gain through stealing of copper ground wire. And this all occurred within a 5-week period. We're pretty certain that all the thefts occurred between midnight and 5 a.m., but the only one we know for sure is that they accidentally cut a fiber optic cable at one of the turbines, and it was at 2:26 a.m. Other than that, we're just guessing as to the time. Now, the thieves really created havoc at this 55 tower wind farm. The very first incident, they broke into 3 wind turbines. The second one, which occurred the next day, the next night, was impacted 4 turbines. The third one was 10 days later. that impacted 4 turbines. The fourth, 4 days later, 6 turbines. Fifth, 2 days later, 6 turbines. The sixth was 8 days later, 2 wind turbines. And the seventh was 9 days later, which was a total period of about 5 weeks. 2 wind turbines were impacted, one of which was also involved in the very first incident. So what the thieves did is that if you look at the photograph on the right, it shows the entry door to the tower, and there's a latch and a padlock. So what they did, and we do know this is fact, that the culprits used a battery operated grinder to cut off the latch and padlock to gain entry. Once inside, from each of the turbines, they stole 50 feet of the bare copper cables and 190 feet of insulated ground cables. Now, the reason why we do know that they were used a battery operated grinder is after the first 2 thefts, the RCMP found some of the stolen copper wire, which was identifiable by the particular jacket or insulation on the insulation covered cable. So what they did, they found it. They charged 3 adult males for the first 2 break, enter, and thefts. But the bad guys were released after being charged to await trial. So guess what happens? The thefts continue. And that's probably why there was a 10-day period in between the second and third incident. Now I'll be commenting on the ventilation screen that you see in that photograph on the right later in this brief presentation. So the immediate steps ought to have been taken to mitigate the financial impact of these thefts. And that's been commented on previously in this presentation. But in this instance, it's much easier said than done. We had a continuous occurrences. They had to take steps to prevent further thefts once they did do any type of temporary or permanent repair. But here's what actually was done. The theft was reported to the RCMP. Steel boxes were welded over the latch and padlock of each entry door, and certainly they paid attention to the towers that were not impacted firstly, to avoid a theft. But what happened was that the thieves, instead of that, prevented them from cutting off the lock and latches, so they removed the ventilation screen, got inside the towers, and were able to open it from the inside because it's an emergency access, and it can't be locked from the inside. So right now we're going to have a little bit of a question for you to give us your views on what you think should have been done to mitigate and prevent the further losses from occurring. So this is being done by our London office. And I'm not sure if you can see it or not.
Hi Wally, this is Robert. I'm seeing the results here. So far, it's 37% of the vote is infrared surveillance cameras at each wind turbine. The next highest answer is weld boxes over the door latch and secure ventilation vents. And the third highest one is all of the above.
Okay, so was there any just strictly for the high voltage?
2% were for high voltage.
Okay. So the majority was the cameras and what?
The highest one was infrared surveillance cameras, and the second highest was weld boxes over the door latch and secure ventilation vents.
Okay, alrighty. Now, how do I get back into my presentation? Okay, so now we've received your responses. The cameras and the metal boxes were the most voted on, with the infrared cameras being number one. And there's 2% of you that wanted to fry anyone that tried to get into the turbines, which probably is a little bit of a joke, but anyway, we just thought we'd throw that question in. So the coverage issues on this is that we had to determine a number of occurrences that would be subject to policy deductible, and I'll get into that in a little bit. And then, you know, we needed to determine a reasonable period of time needed for temporary repairs and eventual permanent repairs to be completed, and apply the policy waiting period for the loss of revenue for each of the wind turbines impacted by the theft. Now, this slide's going to make a little more sense going forward. So when the claim was presented, it was the claim was presented 2 months after the very first incident. That's number one. And at that time, and we're going to be commenting on this, at that time, the permanent repairs were being initiated. So that would have been 8 weeks that the wind farm would have been down, which would stretch into a 10-week period with the repair period. So what we had is that we had physical damage to the towers that was initially estimated at $160,000 after application of a single deductible, and we had a reported business income loss just less than $1 million after paying the 5-day waiting period. It did end up that there were 7 separate occurrences with the physical damage per occurrence being below the policy deductible. So that claim was under deductible. However, the most important thing is that there is no temporary repairs attempted or completed on behalf of the policyholder after the loss occurred. That stated before, it wasn't reported until 2 months after the first theft. So what was done is that we had to determine what the cost of temporary repairs would have been had they been done in a reasonable period of time, and the individual turbines put back into service to reduce the business interruption loss. Now, the cost of doing temporary repairs would be an increased cost of working. So we did agree with the owner of the wind farm, and the final settlement was agreed at $200,499 Canadian. This is strictly the business interruption portion of the claim that was initially reported right around the $900,000 mark. However, there was a reduction because of lack of mitigation on this, which is an important issue, because not only do you have to mitigate, but you have to be able to mitigate safely in that. And we used our electrical engineers to come up with a scope, repair period, and schedule that was negotiated with the insured to derive that final settlement. So, loss prevention. Yeah, the thieves used a battery-operated grinder to cut off the door latch to gain entry. So therefore, steel protective cover was welded in place, covering the door latch, and this did prevent any further loss from occurring as a result of that entry. But then they did smash the vent, went in and opened the door for the other bad guys. And this was remedied by welding steel mesh. And at that time, they also did install wildlife battery-operated infrared cameras mounted high enough that the bad guys couldn't easily get at them. So what has happened here is the police have charged the 3 adult males with theft. We're not certain if they're convicted or not. The police was requesting restitution of all damages. However, recovery is highly unlikely. The bad guys, and we did get some preliminary information from the RCMP on them, were unemployed, had no assets, beat up trucks, and so therefore any type of recovery was highly unlikely. Now, we did also have to deal with another issue, and that was the service agreement with the operator of the wind farm. And there was a possibility the owner may have been able to pass on some of their financial loss that wasn't covered by insurance to them, but they elected not to maintain a really good working relationship. And the fact that the havoc created by the bad guys was really unusual, and they had no contingency plan to deal with that at that time. And as a matter of note, the salvage value of the stolen copper was determined to be less than $10,000 Canadian, and likely impacted that wind farm for a financial loss of over $1 million. Thank you.
Thanks, Wally. Hello, everyone. I'm Chris Davies, Executive General Adjuster for Charles Taylor, based in Toronto. I've chosen this onshore case example because it required a good deal of detective work concerning a claim that was made 6 months after the damage was repaired. Now, in this case, it was necessary to look at systems telemetry to understand the sequence of events in the run-up to the damage, and it yielded some interesting facts on the prospects for recovery. Now, this case concerned a wind turbine creating a power output of 2.3 megawatts, operating with 3 rotor blades, approximately 100 meters in diameter, so pretty small in comparison to the giant offshore models that were spoken about earlier. This diagram is a cross-section of the nacelle. In summary, the yaw ring and 2 yaw gears needed to be replaced because of damage to the gear teeth. The yaw ring and a typical yaw gear are identified as items 15 and 16 on the chart. The function of the yaw mechanism is to rotate the nacelle into the wind in order to optimize the turbine generating capacity and to angle it away from the wind to prevent damage if the wind speeds are too high. In this model, there are 8 yaw gears, such as the one depicted in this diagram, which are essentially motorized mechanisms fitted with hydraulic brakes that rotate the yaw ring. The yaw drives are linked to SCADA, which constantly records turbine data from the turbine. Now, in this case, the manufacturer of the turbine was also the systems operator, and the manufacturer was contracted under a service and maintenance agreement. The owner recorded a SCADA overheating issue with respect to the yaw gears on day 1, which is the baseline date for recording of damage. The service provider's technicians inspected the yaw gears this same day and adjusted the brakes. The turbine was then placed back into service. The 4th annual inspection of the turbine was carried out by the service provider's technicians between day 7 and day 12. During the annual service, the technicians noticed 2 out of the 8 yaw gears were damaged, but didn't notice any damage to the yaw ring. The turbine was again placed back into service. On day 16, a second overheating error was flagged up on SCADA, and the yaw gears and yaw ring were replaced on day 20 following identification of damage. and the shards shown here were collected after the yaw ring was replaced. The shards clearly matched the yaw teeth, and the yaw gear on the right was seized by the manufacturer, who, remember, was also the operator, and taken away for examination. Now, getting hold of those results would have entailed signing a non-disclosure agreement, effectively meaning that we couldn't use the information against the operator, though we actually never got to see those results anyway. So all we had to rely on was the evidence of damage to the yaw ring, the shards left behind, and the SCADA data to piece together what had happened. Like all good investigations needing root cause analysis, we engaged forensic engineers. Case crushing of the teeth was diagnosed by the forensic engineer. Now, there are two plausible explanations for case crushing, one being metallurgy of the damaged teeth, and two, overloading of the teeth. After reviewing the SCADA data and on the balance of probabilities, it was decided by the forensic engineer that case crushing was caused by incorrect application of the braking mechanisms. And the claim was paid, including the business interruption component, as the all risks policy didn't exclude this type of damage. We then needed to look at the prospects for recovery. And the manufacturers made a promise of a robust and reliable design, and that the model was designed to last. But the preferred explanation of the forensic engineer precluded any prospect of recovery against the manufacturer, particularly as the damage occurred 1 year out of warranty. We then looked at the performance of the service provider, who, remember, was also the manufacturer and also the supplier and installer for the turbine, for a potential failure to detect damage during inspection of the brakes and during the annual inspection. So we called for the service and maintenance agreement, and these three clauses stood out. Firstly, there was a waiver of subrogation. Secondly, the only obligation on the service provider was to re-perform or correct any non-conforming service. Thirdly, the service provider was only responsible to the owner for reimbursement of up to $100,000 of the deductible. Now, taken as a whole, the agreement was seen as providing clear evidence of the parties' intentions to make the all risks property insurance responsible for loss without any chance of subrogation. So in the end, we had no prospect of recovering any of insurers' outlay from the operator. So my advice when considering recovery is to get hold of the service agreement early and to evaluate the recovery prospects from there. So that brings me to the end. Thank you for listening. I'll field any questions at the end.
Thanks so much, Christopher. That's, and all of the presenters. That was very, very interesting. And we have a number of questions. I think we'll start off with one for Ed. It's probably the best to answer this one since it came up in his presentation. And that is white etch cracking the same as stress corrosion cracking that is seen in other metals from moisture and stress?
That's a great question. Thank you. If I'm honest with you, firstly, I must confess I'm not a metallurgist myself. The one thing we can say, without this sounding like a cop-out of an answer, is the fact there are currently, I think at the last guest from talking to an expert, about 15 possible scenarios which can create white edge cracking. It's possible that some of those are certainly fall within that matrix of possibilities. However, I couldn't definitively confirm if they are, but what I can say is that the cause mechanism or failure mechanisms you've just described are not the exclusive reasons for them.
Okay, thanks, Ed. I think while you're on the line, this one might be good for you as well, and that's for a similar physical damage claim onshore versus offshore. What would you say is the additional cost to do the repair offshore on a percentage basis?
Again, another great question. I think it's always one of those things. It's very difficult to say what an average claim cost would be. But I think if we just take a generic, very high level figures, I would say, broadly speaking, probably 10 times. If we think that pretty much any minor, for example, cable replacement or damage in an offshore wind farm is probably looking at 2 to 4 million euros. And obviously the materials to do that, as in the cable itself, probably represent 10% of those costs. The rest of it is vessel costs, personnel costs, and the like. And clearly the big difference between the offshore and the onshore cost regime is chartering vessels, and that is always where the lion's share of the costs sit.
Excellent, thanks. I'll open this up to any of the panelists that want to answer it. So the question is, given the SCADA systems in wind turbines and the value of them, are you aware of any coverage available for physical damage from cyber attack?
I'll jump into this here from London. As again, obviously, as an adjuster, clearly, can't comment on maybe the intention of insurers going forward. I am aware loosely that that cyber coverage is something which is looked at. It's not something we've ever seen actively presented as either as a claim or specifically in a policy. But that's not to say it won't be. I'm sure it is an area which is being looked at. But I know it's quite a challenging area in general. But that's all I can say from our limited observations of the European/UK market.
Great, thanks, Ed. So another question here, I think for yourself as well, Ed, and that's, have you been successful in having manufacturers step forward and pay claims for common design workmanship issues without the necessity for a claim to be processed?
Hi, Robert. Yeah, thanks. This is Neil Armstrong here. Yeah, so in my dealings with kind of mid-scale onshore wind and solar to an extent as well, yeah, often we do see claims where the OEM has picked up the damaged items under warranty. I mean, I'm actually dealing with a wind farm in Canada at the moment where the manufacturer is covering the physical damage costs for replacing some damaged blades and yaw rings. What we generally get presented with then is the business interruption claim. The policy wording that I'm specifically working under specifically covers business interruption where the physical damage costs have been picked up by the manufacturer. So in general, I would say with the larger scale manufacturers, they are reasonably good at honouring their warranties and covering, you know, a damage that's attributable to defects or poor workmanship. However, on the small scale side of things, I have had some interesting claims where, on the very small scale side of things, kind of local service providers that should offer warranties have kind of reneged on their warranties, and that can cause some issues in coverage. So yeah, that's kind of my observations from the claims I've handled.
Okay, thanks for that, Neil. Appreciate it. So we have another one here that's it goes back to the white edge cracking. It's a little bit of a nested question, so it might take a minute to decipher, but essentially what the question is, surface were we looking at, first of all, for the white edge cracking under the electron microscope, and was it a bearing? And what component is most susceptible? Finally, has anyone reviewed metal supply sources and frequency of occurrence?
Okay, as you said, yeah, there's a couple in that. I think the first point, I'm not quite, Robbie, you might need to repeat that. Was the first point about what surface was that?
Exactly.
Okay, that was taken from a cross section of a bearing, which brings into the probably jumping to the third, well, possibly the second point, is the areas we find which are most susceptible to that, and it is a phenomenon which occurs almost exclusively in roller bearings or bearings in general, whether they be taper bearings or whatever they may look like. But typically, it is a bearing-based phenomenon. It is seen in other industries as well. I mean, certainly the offshore industry, which uses vessels and uses thrusters, i.e. things which rotate under load, that's certainly been seen before in other rotating machinery, but it's really only come to prevalence with wind turbines, both onshore and offshore, given the volume of gearboxes which are placed under load in these particular axial loads. To cover, I think, the final question in that, which was metal supply. Yeah, absolutely. We have one case at the moment with a wind farm which has white edge cracking in gearbox bearings from two different manufacturers from two different sources of the stock metal. So it's something which is being looked at. And as I said, I must stress I am not a metallurgist, so I can't give definitive answers. However, I am reliably informed by our retained metallurgist on this claim that there are, as I said, 15 or so possible different scenarios which can contribute to the formation of white edge cracking, and those have yet to been fully bottomed out as to one. But it seems to be very much a combination of factors which when brought together can create this phenomenon. What I would say, it seems to be quite an area of interest, and I understand that from the audience. And so there's certainly information, there's an open source information on the internet which I would direct people to, specifically if you wish to learn a little more about it.
That's fantastic. Actually, I think that kind of brings me to my next point, which is we will be sending out an email tomorrow, which I mentioned at the beginning, which will have this recording. And we have got a number of additional questions, but since we're already 10 minutes over, I think we should probably cut it off there. But what we could do is we can answer those questions, and we can include that in the email that we send out tomorrow. And then we could also include the link that Ed was speaking about there. So I think